The partial derivative examples that we've worked with so far have all been for one simple function, a curve, z equals x squared minus y squared. Let's go a step further now and look at some more challenging examples. So let's say we have a cylinder. The volume of a cylinder V, which I've shown in blue, is equal to pi r squared, radius squared, L, length. So the volume of a cylinder is a function of pi times the radius squared times the length of the cylinder. If we're interested in knowing how the volume changes as a function of length, we can use partial derivatives to do that. So specifically, del V del L, the partial derivative of volume with respect to length for a cylinder, is described by pi r squared and then the derivative of length. So now you might think, oh, I thought that we held other variables constant. Well, that only is true if they're a separate term. So if there's a plus sign or minus sign, if that isn't the case, separating the two variables. So in this case, we're adjusting volume with respect to length, but the radius matters because radius influences length's impact on volume. They're not separate terms, they're all part of the same term. So what this means is r is definitely involved here, radius is definitely involved, and when we take the derivative of L, so we don't take the derivative of r, we just treat it as a constant relative to L, but when we take the derivative of L, following the power rule, this becomes 1L to the power of 0, and anything to the power of 0 is equal to 1, and so we're left with pi r squared. So this is interesting. It's quite different from what we were seeing earlier with z equals x squared minus y squared, because now the partial derivative of volume with respect to length is dependent on another variable, on a third variable that isn't length itself. So what this means is that a change in length L corresponds to a change in volume by pi r squared. Let's look at a hands-on code demo to make sense of this. So as we've already covered in the slides, the volume of a cylinder is described by V equals pi r squared L, where r is the radius of the cylinder and L is its length. So let's create a Python function that contains all of that equation. So the math library contains a pi constant, and we multiply that by r squared and by L. So let's say that the radius, for the sake of argument, is 3 meters. So we set a torch scalar tensor equal to a float value of 3, and we require gradients for this because we're going to be calculating gradients. And let's say that the length is 5. So we create a scalar tensor L that stores that 5, and again we turn gradient tracking on. Then the volume of the cylinder, we can calculate that by passing R and L into the cylinder volume equation. And so we can find out that, all right, with a radius of 3 meters and a length of 5 meters, a cylinder has a volume of 141.4 meters cubed. So as we've done in PyTorch in the past, to calculate slopes of V with respect to any of the variables, R or L, in the equation here, we can compute the autodifferentiation backward from V back into this formula, and we can determine that, okay, the gradient of V with respect to L at this point, at the point where the radius is 3 and the length is 5, is equal to 28.3. So the impact of this is that if we increase length by L at the particular radius that we were using in the code demo, if we increase length by L, where the radius is equal to 3, then that's going to increase the volume of the cylinder by 28.3. Okay, so that gives us v with respect to L, but how about v with respect to r, so volume with respect to radius? So again here, we can use our pi r squared L function as a starting point. L is a part of the same term with r, so we leave it in there as a constant, and we calculate the derivative of r squared. And that comes out by the power rule to 2r. And simplifying the way that this looks a bit, then we know that del v del r is equal to 2 pi rl. What this means is that a change in radius r by an infinitesimally small amount corresponds to a change in volume by 2 pi rl. So why did I add in this qualifier of by an infinitesimally small amount? Well, this is, first of all, related to the calculus of infinitesimals that we've been talking about from the beginning of these live lessons, that term that Leibniz coined to describe this whole subject area of the study of rates of change. And this concept of infinitesimally small comes into play again here because as r varies, it has an impact on the partial derivative itself. So this might be a little bit hard to wrap your head around in the abstract. Let's look at a hands-on code demo with numbers to make this a bit more concrete. So as we had in the slides, for changes in v with respect to r, we have the following equation, del v del r is equal to 2 pi rl. So we already earlier calculated v backwards, so we already performed auto differentiation on volume. So assuming we want to be at the same point where the radius and length are the same as we were looking at earlier, and that's fine, let's do that. So radius is 3 meters and length is 5 meters. This means that at that particular point, an infinitesimally small change in r has an impact of this slope of 94 on volume. And so instead of using PyTorch to calculate it, as we already have, so by auto-differentiating on v backwards, and then asking for the slope of v with respect to r by asking for the grad attribute of the r tensor, we could also have calculated this same slope manually by using the formula that we have from the slides. So at this particular point, the slope dv dr is equal to 2 pi rl, so 2 pi rl. At this particular point, with our radius of 3 and length of 5 that we've been using for all of our examples so far on the cylinder, we get the same slope. So again, PyTorch just makes things automatic and easy, so we don't have to do all these derivations by hand. But the derivations come in handy, of course, for learning about what's going on under the hood in PyTorch. Since r is included in the partial derivative, adjusting it affects the scale of its impact on volume. So it's our first example of this in this notebook, but it's actually the norm in calculus. So this means that the derivative only applies at an infinitesimally small difference in r. And so the smaller the delta r, the closer it will be to the true dv dr at that infinitesimally small point. For example, at a delta r of 1 times 10 to the negative 6, so a very, very small delta, we can use our cylinder volume calculations to see what cylinder volume would be if we add the delta to the radius versus not, and we see that that comes very, very close to this 94.25. But the larger you make this delta, the less this will hold true. All right, nice. So we've got a better understanding now of partial derivatives than ever before. Let's look at a few more relatively advanced examples, a few exercises to test how well you're grabbing this stuff.